Right now, as you read this, the solar system is falling through a cavity in space so wide that light itself takes 1,000 years to cross it. You did not choose to be inside it. You were born inside it. Your parents were born inside it. Every human who has ever lived, every civilization, every war, every sunrise anyone has ever watched, has happened inside this hole. And in 2022, a team of astronomers at the Harvard and Smithsonian Center for Astrophysics published a paper in Nature that mapped its walls for the first time. They found something the press releases quietly refuse to shout. The cavity is not a static feature of the sky. It is expanding. It is still expanding. And the walls of it are moving outward at roughly 6.5 kilometers per second, which means whatever carved this hole is not finished. That is your 150-word warning. Now let me tell you what it means. Before I go any further, I want to know where you are watching from tonight, what time it is where you sit, whether anyone ever told you in school, on television, in any documentary you have ever watched, that Earth does not orbit the sun through ordinary space. Because I was not told either. I had to find it in a peer-reviewed paper, and once you see it, you cannot unsee it. The public version of our address in the galaxy is simple and calming. Third rock from the sun, middle of a quiet spiral arm, boring suburb of the Milky Way. Nothing to worry about. That framing is not wrong, exactly. It is just softened almost to the point of dishonesty. Because the truth, the version scientists have been quietly refining for decades and finally mapped with precision using data from the European Space Agency's Gaia satellite, is that our solar system is currently crossing the interior of what astronomers call the local bubble. A cavity roughly 1,000 light-years across, carved out of the dense interstellar medium of the galaxy, a hole, a wound. Every constellation you have ever learned to recognize sits either inside this cavity or on its walls. The nearby star-forming regions astronomers point telescopes at, the Orion Nebula, the Taurus complex, the Ophiuchus cloud, without exception sit on the surface of this hole. They are lined up around the edge of an explosion. That is the reversal I want you to hold. You are not looking at random stars in random directions. You are looking at the inside of a blast crater. The 2022 paper, led by Catherine Zucker and her colleagues, did something no one had ever done cleanly before. They used the Gaia satellite's precision three-dimensional map of nearby stars and molecular clouds to reconstruct the shape and motion of the bubble's surface. They tracked the expansion, they ran the physics backward, and they estimated that the bubble began forming about 14 million years ago, when a sequence of massive stars, at least 15 of them, detonated as supernovae in the same region of space, pushing gas outward in a single expanding shockwave. That shockwave is what carved the cavity. That shockwave is what you are still inside of. 14 million years is not long, in cosmic terms. It is roughly the age of the Antarctic ice sheet in its current form. Our own species, anatomically modern humans, has existed for about 300,000 years. The bubble has been here 46 times longer than we have. And it is still moving. Now here is where the story starts to change. Because a bubble that is still expanding is a bubble that has not yet reached equilibrium, which means the pressure that carved it is still, faintly, in motion. Which means the wall between us and the rest of the galaxy, the denser interstellar medium beyond, is not a permanent architectural feature of our sky. It is a moving front. And on the other side of that front, when we eventually reach it, or it eventually reaches us, is space that behaves differently. Denser, colder, full of particles our solar system has not had to negotiate with in millions of years. The comfortable frame says space is empty. The evidence says space is scarred, and we are living inside the scar. Let me put that in a way that stops feeling abstract. The Heliosphere, the invisible bubble our sun inflates with its solar wind, extends about 120 astronomical units outward. Every cosmic ray that reaches your body has had to survive 2 layers of shielding. The heliosphere is one. The local bubble's low-density interior is the other. Thin either one, and the numbers on the ground change. That is not speculation. Voyager 1 crossed the heliopause in 2012, Voyager 2 in 2018. Both recorded a sudden jump in galactic cosmic ray flux the moment they left the Sun's protection, on the order of 20 to 30%. That is what unshielded interstellar space looks like during a relatively calm era for our star. Now think about what that means. The bubble is expanding. The heliosphere fluctuates with the solar cycle. Earth's magnetic field, the last layer of shielding, is measurably weakening. All three of our defenses, the ones our biology, our infrastructure, and our entire civilizational math depend on, are variables. Not constants. Variables. And this is the thesis I want you to carry through the next 9 chapters. The version of space you were taught in school, quiet, empty, safe, is a temporary configuration. The version the data actually describes is a fading shockwave, a thinning shield, a compressing bubble, and a species that arrived during the calmest window and mistook the calm for the rule. To understand what that means for you, for the people you love, for the century you are trying to plan your life inside of, we first have to go back to what carved this hole in the first place. Because the answer is worse than a single explosion. The answer is a chain of them. And the same physics that made us possible is the same physics that will, eventually, come back around. If you look up the local bubble in a general audience science article, you will find something calm, a pleasant graphic, a short paragraph about how our solar system happens to be traveling through a region of lower than average gas density, a friendly line about how this makes it easier for astronomers to see nearby stars because there is less dust in the way. And then the article will move on, as if that were the whole story. That is the story the public gets. It is not a lie, it is a curation, and the curation matters, because in the peer-reviewed literature, in the Zucker Papers appendices, and earlier work by Rosine Lallemant, the tone is different. You find phrases like superbubble, sequential supernova activity, estimates of the total energy required to carve this cavity on the order of 10 to the 51 ergs, released over 14 million years. 100,000 times the Sun's entire lifetime output dumped into our neighborhood. The public version says quiet neighborhood. The technical version says crime scene. Let me be clear about what I'm not saying. Nobody is hiding anything. The papers are public. The data is on ESA servers tonight. The problem is translation. Between what specialists know and what the public hears, there is a compression layer applied for decades that produces a version of the sky no working astrophysicist would defend at a conference bar. Here is the crack in the reassuring frame. If our neighborhood is quiet, why is it a cavity? Cavities are not the default state of the interstellar medium. The default state is denser, full of gas, dust, molecular clouds. That is the ordinary weather of the galaxy. What we are living in is not ordinary weather. It is the calm eye left behind by a series of storms. And when you are in the eye of a storm, 2 things are true at once. It feels calm, and you are surrounded by wall. That surrounding wall is what the Zucker paper mapped. And when you look at the map, when you see the 3-dimensional reconstruction of where the bubble's surface actually sits, the image changes something. You realize that everything humans have ever pointed a telescope at, in the sense of nearby star formation, sits on that wall. The Taurus molecular cloud, the Ophiuchus complex, the Chameleon region, the Corona Australis. These are not independent features scattered across the sky. They are compression fronts. They are places where the bubble's outward shockwave, over millions of years, ran into denser interstellar gas and squeezed it hard enough to trigger new star formation. The stars being born in our neighborhood right now are being born because of the same explosions that carved the hole we are living inside. That is the deep unity of the picture. We are not adjacent to those nurseries. We are causally linked to them. The same event that made our current address possible is also the event that is still, at the edges, making new suns. That is beautiful, in a way. It is also uncomfortable, because it means the local bubble is not a special feature. It is a snapshot of a process, and that process, sequential star formation, followed by sequential supernova activity, followed by cavity carving, followed by compression-triggered new star formation, is how large regions of the galaxy actually work. The Milky Way is not a smooth disk of evenly distributed gas. It is a foam, a Swiss cheese of bubbles, some old, some young, some overlapping, some in the process of merging. Astronomers have names for them. The Loop 1 superbubble, right next to ours, is thought to be interacting with the local bubble along a compressed shell of gas. The Orion Eridanus superbubble is another. There are dozens of these features in the galaxy's disk, and the local bubble is just the one we happen to be inside. Which means the piece we are experiencing is neither special nor permanent. It is a rotation. It is our turn. Now, let that sit for a second. Every mass extinction event on Earth over the last 500 million years has happened while the solar system was moving through some particular region of the galaxy. Some of those events correlate, weakly but persistently, with the solar system's passage through spiral arms, where supernova rates are higher. Some correlate with periods when Earth appears in the geological record to have been dusted with elevated levels of iron-60, a radioactive isotope that is essentially a fingerprint of nearby supernova activity. The layers of iron-60 in deep-sea ferromanganese crusts are dated to roughly 2 to 3 million years ago, and also to about 6 to 7 million years ago. Those dates are inside the window when our solar system is thought to have entered and been moving through the local bubble. Read that again. The last time Earth was measurably dusted with the debris of an exploding star was during the emergence of the genus Homo. Our ancestors were walking under a sky that was, in a very literal sense, still glowing with the aftermath of a stellar explosion. And it left a chemical signature at the bottom of the ocean that we can still measure today. That is not a metaphor. That is a laboratory result. The rocks remember. So when someone tells you that our solar system is passing quietly through a stable neighborhood, understand that the neighborhood only looks stable if you zoom in on the last few thousand years. Zoom out to the last few million, and you are watching a solar system move through the smoldering remains of a stellar battlefield, occasionally picking up radioactive dust from the corpses of stars that died before our species existed. That is the story NASA does not tell you in the Instagram caption. Not because NASA is lying, because the Instagram caption is not built to hold that sentence. And now that you know it, we can go to the next question. What actually carved this hole? Because it was worse than one explosion. It was a chain. Here is the mechanism. And I want you to follow it carefully, because once you understand how the bubble was made, the rest of the story becomes almost impossible to unsee. Roughly 14 million years ago, in the direction we would now call the constellations Scorpius and Centaurus, a large cluster of young massive stars was doing what massive stars do, burning fuel at a violent rate, racing through their short lifespans. A star roughly 10 times the mass of the Sun does not live 10 times shorter than the Sun. It lives about 1,000 times shorter. Instead of 10 billion years, it lives about 10 million. It burns hot, blue, and brief, and when it runs out of fuel in its core, it does not fade gently. It collapses inward at a fraction of the speed of light, rebounds and detonates as a Type II supernova. That single detonation releases in a matter of seconds more energy than the Sun will radiate across its entire 10 billion year life. In seconds. And it does not release that energy in one direction. It releases it as an expanding sphere, a pressure wave of plasma and heavy elements pushing outward through the surrounding interstellar medium. If it happens once, in isolation, it carves a small cavity, a few dozen light years across. That cavity slowly cools, refills, and disappears back into the ordinary weather of the galaxy over a few million years. That would be the normal case. The local bubble is not the normal case, because in the Scorpius-Centaurus association, this did not happen once. It happened, by best estimates, at least 15 times. 15 massive stars born within a few million years of each other, dying within a few million years of each other, each one adding its shockwave to the shockwave already expanding from the previous. Each detonation reinforcing the outward pressure, each explosion pushing the wall of the growing cavity further from the center. What you get from that is not a small hole. You get a superbubble. And superbubbles are the largest coherent structures in the interstellar medium. Now translate the energy scale. The Sun outputs about 4 times 10 to the 26 watts, continuously, for 10 billion years. Take that entire lifetime budget and compress it into a burst that lasts a few seconds. That is a single supernova. Now imagine that scream 15 times, aimed outward from a single point. That is what carved the local bubble. The atoms in your body heavier than hydrogen, the iron in your blood, the calcium in your bones, the oxygen you are breathing, were forged inside stars that lived before the Sun and were scattered by explosions like these. You are made of supernova debris. That is not poetic exaggeration. In 2016, a team led by Anton Wollner in Australia published a landmark paper in Nature. They analysed deep-sea ferromanganese crusts and cores from 3 different ocean basins. They looked for iron-60, an isotope of iron that is produced almost exclusively in massive stars and their supernova explosions, and which has a half-life of about 2.5 million years, which means any iron-60 you find on Earth today had to arrive here recently, in geological terms, or it would have decayed away. They found it, in distinct layers, concentrated at depths corresponding to about 2 to 3 million years ago, and another older layer at about 6 to 7 million years ago. That is a direct chemical fingerprint. The bottom of the Pacific Ocean holds the fallout of nearby supernova explosions that happened while our human ancestors were still learning to walk upright. The rocks caught the dust. Follow that logic to its endpoint. If we can measure fallout from those explosions today, that means the debris reached Earth. It passed through the Heliosphere. It made it to the surface. It settled into the ocean. It got mixed into geological layers. It is now part of the planet's material record. Now compare that to the 1987A supernova. That is the supernova that briefly became the most famous event in astronomy in the late 20th century. Amateur astronomers around the world could see it with their eyes. Neutrino detectors on Earth picked up its ghostly signature hours before the visible light arrived. It was, at the time, treated as a once-in-a-lifetime spectacle. 1987. A was 168,000 light-years away, in the large Magellanic Cloud, a satellite galaxy of the Milky Way. It was not even in our galaxy, and it was still spectacular. The supernovae that carved the local bubble happened within a few hundred light-years of the Sun, in the same galaxy, in our neighborhood, and there were at least 15 of them. If 1987A was a distant firework, the sequence that made the local bubble was a bombardment. Here is the part that should bother you. The physics that produced 15 supernovae in one small region of space in 14 million years is not a physics that has stopped. Massive stars are still being born. They are still going to die. The Scorpius-Centaurus association is not empty. It still contains young, massive stars that will, on their own individual timescales of a few million to a few tens of millions of years, detonate. The nearest known candidate for a nearby supernova, Betelgeuse, sits about 600 light-years away. Not close enough to be catastrophic, just close enough to be, when it goes, spectacular. But Betelgeuse is not the only candidate, and the bubble we live inside is not a permanent building. It is a shockwave in slow motion, which means the walls, the ones we have not reached, are the tombstones of stars that went before, and the next round of explosions has not happened yet. If this hole is still expanding, then something is still pushing on it. And whatever it is pushing against, we have not met yet. Now that you know how the bubble was made, I want to show you the part almost no popular account will discuss. The part that reframes everything you just heard. The local bubble is not a fortress. It is not an armored shell around the solar system. It is a low-density cavity, which means, physically, it is defined by what is missing. There is less gas inside it than in the surrounding galaxy. Less dust, fewer particles, and that reduced density is what makes it feel like protection. But protection by absence is not the same thing as protection by structure. Let me put this in a way that lands. Imagine you are told you have a security system, and when you ask what it is, You are shown a room that just happens to be, statistically, quieter than the rooms around it. That is not a security system. That is a lucky room, and luck can end. The Heliosphere, the smaller bubble our sun inflates with its own solar wind, is the actual last line of defense before Earth's own magnetic field takes over. The Heliosphere pushes outward against the interstellar medium. It carves its own little pocket, roughly 120 astronomical units in radius, inside the larger local bubble. And here is the part that matters. The size of the Heliosphere depends on the pressure balance between the solar wind pushing outward and the interstellar medium pushing inward. Change either side of that equation, and the Heliosphere resizes. The local bubble's low density is what allows the Heliosphere to inflate as large as it currently is. Move into a denser region of interstellar gas, and the Heliosphere compresses. Compress the Heliosphere, and more galactic cosmic rays reach Earth's orbit. That is not a hypothesis. That is what Voyager 1 and Voyager 2 measured the moment they crossed the heliopause. Cosmic ray flux jumped, sharply, immediately. Because outside the Heliosphere, even inside the local bubble, the background radiation environment is measurably harsher. NASA's Interstellar Boundary Explorer, IBEX, has been measuring the shape of the heliopause since 2008. The boundary is not a clean sphere. It is asymmetric. It has ribbons of enhanced particle emission we still do not fully understand. Our shield is a dynamic interface whose shape depends on the interstellar medium we happen to be crossing. Change the environment, and the shield changes with it. Here is the fragility. The Sun's magnetic activity is not constant. It cycles on an 11-year rhythm, and it cycles on longer rhythms of centuries and even millennia. During periods of low solar magnetic activity, the heliosphere weakens, which means during low solar activity, more galactic cosmic rays reach the inner solar system. This has been measured. This is standard heliophysics. Neutron monitors on Earth's surface see the cosmic ray flux rise and fall with the solar cycle, and the anti-correlation is clean. The Maunder minimum, from roughly 1645 to 1715, is the most famous example. Sunspots almost vanished. Cosmic ray flux at Earth rose. We can measure this today because cosmic rays produce beryllium-10 in the atmosphere, which gets trapped in ice cores. Drill Greenland ice from that era, and you see the spike. The sun went quiet. The shield thinned. The particles rose. We are not currently in a Maunder-style minimum, but solar cycle 24, the one that peaked in the early 2000s, was one of the weakest cycles in a century. Solar cycle 25, which we are inside now, has been active but not extreme. And some solar physicists have been quietly discussing whether we are entering a longer-term phase of reduced solar magnetic output. If we are, the heliosphere will, on average, be smaller and weaker for the coming decades, which means more cosmic rays, which means more radiation exposure. Not tomorrow, not next year, but cumulatively, measurably, and on a trajectory nobody in the public conversation is really tracking. Now stack the layers. The local bubble is expanding, which over long timescales means its interior is diluting further, which is good for shielding, right? Yes, in the short term. But the same expansion means the bubble is aging, cooling, and eventually the pressure that maintains its cavity structure will fade. The sun's motion through the bubble is also carrying it toward denser regions of interstellar gas. And within the bubble, the sun has already entered a small denser region called the local interstellar cloud, roughly 60,000 years ago, which we will discuss later because the implications are worse than they sound. The point is this. We have three layers of shielding. Earth's magnetic field, the heliosphere, the local bubble's low-density interior. All three are dynamic. All three are variables. And all three, on different timescales, are showing signs of stress or drift. That is not a fortress. That is a stack of overlapping tarps in a rainstorm. Any one of them can shift. And when they shift, the water finds you. Here is the blunt verdict. The reason your body has never been shot through by a stellar bullet at any meaningful rate is not because space is safe. It is because you happen to have been born during a specific configuration of overlapping shields that all happen to be simultaneously in a reasonably strong state. That configuration is not guaranteed. It is not paid for. It is not maintained by anyone. It is the current weather. Now here is the pivot. If the shielding is variable, if the numbers on the ground can rise, then everything downstream of those numbers, the biology, the electronics, the infrastructure, the missions we plan to send further out, all of it is exposed to a variable we have been treating as a constant. And that is where the math starts breaking. Because a small ship going through a thin wall is nothing dramatic. A bigger ship, a longer mission, a farther journey through the same thinning environment becomes something else entirely. It is not a linear scaling. It is a category change. I want you to break one intuition tonight. The intuition that says a longer trip is just a longer version of a shorter trip. A farther mission is just a scaled-up version of a nearby one. More radiation is just a small percentage more than what we already handle. That intuition is wrong, and it is dangerously wrong. Here is the actual math. An astronaut on the International Space Station orbiting inside Earth's magnetosphere at an altitude of roughly 400 kilometers absorbs between 150 and 200 millisieverts of radiation per 6-month rotation. That is already about 50 times the average background dose a person on Earth's surface receives in a year. 50 times. And that is with the magnetosphere still doing most of the work. The station is technically in space, but it is still inside our planet's magnetic bubble. Now compare that to what happens the moment a crew leaves low Earth orbit. Once you cross the Van Allen belts and enter deep space, you lose the magnetosphere. You are still inside the heliosphere. You are still inside the local bubble. But you have shed the innermost layer of shielding. NASA's Human Research Program has estimated, based on measurements from the Curiosity rover's radiation detector during its 2011 to 2012 cruise to Mars, that a crew on a similar transit would absorb roughly 300 millisieverts on the way there. Not counting time on the Martian surface, not counting the return trip, just the outbound leg. A full round trip with a stay on the surface is estimated at 600 to over 1,000 millisieverts total, depending on solar conditions and mission duration. 1,000 millisieverts, 1 sievert. Now translate that. The lifetime radiation worker limit for occupational exposure in most Western countries is around 50 millisieverts per year, with cumulative career limits typically in the range of a few hundred to 1,000 millisieverts total, and even those are considered generous. A single round trip to Mars, under current heliospheric conditions and current mission profiles, would deliver an entire radiation worker career's worth of exposure in about 2 to 3 years. That is not slightly more radiation. That is a categorical shift into a dose regime we do not routinely allow any Earth-based worker to accept. And that is the number under our current shielding conditions. During a normal solar cycle, inside a normally inflated heliosphere, inside a local bubble that is currently in relatively good shape. Now break the assumption. What happens if the heliosphere weakens by 20 or 30%, which is well within the range of variability we have measured? The flux does not rise linearly, because composition matters. The most damaging component of cosmic rays is not the low-energy stuff. It is the high-energy heavy nuclei, iron, carbon, silicon, oxygen, moving at nearly the speed of light, called HZE particles. Their biological damage per unit dose is far higher than reference radiation. A weaker sun lets in more of the specific particles that do the most damage per hit. Estimates show HZE flux at Earth's orbit rising by factors of 2 to 4 during weak solar cycles compared to strong ones. That is not a 10% problem. That is a doubling to quadrupling of the most biologically dangerous component of your exposure. And you cannot shield against it easily. Heavy nuclei, moving at relativistic speeds, punch through aluminum. They punch through hydrogen. They punch through water. The physics of stopping them requires either enormous mass, on the order of meters of dense shielding, or exotic active systems that no operational spacecraft currently deploys, which means your Mars crew, planned for the mid-2030s, is not being planned against the radiation environment they will actually encounter. They are being planned against the radiation environment we have measured during a specific window of the last 2 decades, and that window may not be representative of the window they fly into. Now scale it further. A Mars mission is 3 years. A permanent Mars settlement is a lifetime. Every year outside the magnetosphere adds cumulative dose. Every year of the settlement is another year of galactic cosmic ray exposure to bodies that evolved inside a stack of shields none of the settlement's inhabitants have. The scale rupture is this. A trip to the Moon is not a smaller Mars mission. A trip to Mars is not a smaller interstellar mission. Doubling the duration of a spaceflight does not double the risk. It multiplies it because dose accumulates over time, and biological damage does not repair linearly. It compounds. Some damage repairs, some does not. Some triggers cascade effects that only manifest years or decades later in the form of cancers, cardiovascular disease, cognitive impairment. Here is the part almost no one says. Apollo astronauts flew short missions, days. That is why the Apollo program never really tested the biology of deep space radiation exposure. The astronauts got out fast. The lunar surface stays were measured in tens of hours. The transits were less than a week each way. It was a sprint. And a sprint through a radiation environment is survivable in a way that living inside that environment is not. Every ambitious human spaceflight goal beyond low Earth orbit, in every serious agency's plans, requires solving a radiation problem we have not solved. And every calculation of how solvable it might be is based on assumptions about the shielding environment that are, themselves, only stable if the underlying physics of the heliosphere and the local bubble stay in their current configuration. That is a lot of assumptions stacked on a lot of variables. Now let me pivot, because this is not just a spacecraft problem. This is a body problem. And the bodies that are already being affected are alive, right now. Some of them have already come home. And what has happened to them, quietly, is more disturbing than the public conversation has admitted. Scott Kelly spent 340 consecutive days on the International Space Station between 2015 and 2016. That is not a Mars mission. That is not deep space. That is low Earth orbit, still inside the magnetosphere, still with most of Earth's shielding intact. And when he came home, NASA subjected him to one of the most intensive biomedical studies ever performed on a returning astronaut because his identical twin brother, Mark, had stayed on Earth as a genetic control. The results were not the reassuring story the public got. Yes, most of Scott Kelly's biology returned to baseline within months of his return. That is the headline. That is what NASA emphasized in press briefings. That is the truth. But it is not the whole truth. Because a subset of his gene expression changes, roughly 7%, did not fully revert. 6 months after landing, his DNA was still expressing itself differently from his brother's in ways that appear to have been persistent and possibly permanent. His telomeres, the protective caps at the ends of chromosomes that typically shorten with age and stress, behaved anomalously. They lengthened while he was in space, then rapidly shortened when he returned, ending up on average shorter than they had been before his mission. That is one man, 340 days, inside the magnetosphere. Now extrapolate. NASA's own studies of rodents at Brookhaven National Laboratory, where researchers use particle accelerators to simulate the specific radiation profile of galactic cosmic rays, have shown measurable cognitive decline. Not death, not obvious injury, just quiet degradation, reduced learning performance, increased anxiety-like behaviors, alterations in the dendritic structure of neurons in the prefrontal cortex, the part of the brain that handles judgment, planning, and decision-making. All this from doses that are relevant to what a Mars crew would actually receive. And here is the image I want you to hold, because this is what these particles physically do inside a human body. A single high-energy iron nucleus traveling at near light speed is essentially a bullet of pure charge and mass. It does not scatter softly like a photon. It punches. It leaves a straight-line track through tissue, ionizing atoms and shredding molecular bonds. In the brain, that track passes through neurons, dendrites, myelin sheaths, leaving a corridor of damaged cells the body cannot fully repair because neurons do not readily regenerate. Now here is the part that will change how you think about astronauts forever. Apollo astronauts, all the way back in the late 1960s and early 1970s, reported a strange phenomenon: random flashes of light inside their closed eyes, especially during the coasting phase between the Earth and the Moon. NASA studied this and eventually concluded that the flashes were the direct visual perception of single cosmic ray nuclei passing through their retinas or their occipital cortex. Every flash was a particle. Every particle was a punch. The astronauts were watching in real time the interstellar radiation environment interact with the tissue of their own eyes. That is what deep space looks like from the inside. Not stars, not silence. Flashes. Constant, quiet, random flashes. Let that sit for a second. Every astronaut who has ever left low Earth orbit, every human who has ever been beyond the shielding of the magnetosphere, has watched their own retinas being struck by supernova debris. Live. Multiple times per hour. Sometimes several times per second during solar events. This is a routine, documented phenomenon. It is in the astronaut biomedical literature. It is in oral history interviews. Buzz Aldrin has talked about it. Michael Collins mentioned it. Every subsequent lunar crew reported it. And we sent them anyway. Because the missions were short. Because the exposure was survivable. Because the math worked, just barely, for a sprint. But we are no longer talking about sprints. We are talking about long-duration missions, permanent bases, interplanetary colonization. And the biology we have on hand does not support those ambitions the way the public conversation implies it does. Here is what a permanent Mars colonist would face. Every day, for the rest of their life, their body would be traversed by these particle tracks. Their brain would accumulate them. Their eyes would accumulate them. Their heart, their blood vessels, their reproductive tissue, their bone marrow, all of it, accumulating microscopic damage tracks that repair imperfectly. The lifetime cancer risk projections from NASA are honest but incomplete because they focus on cancer, which is measurable. What they cannot yet measure, because we have no long-term human population that has lived through it, is the cognitive and cardiovascular decline that shows up decades later. Those studies do not exist yet. The subjects have not lived long enough. And by the time we have data, the first colonists will already be old. And this is with our current shielding. Now recall the previous chapter. If the heliosphere weakens, if the local bubble thins along the sun's future trajectory, all these numbers rise, not slightly, meaningfully. Here is the reinterpretation I want you to carry forward. The bubble is not just cosmic architecture. It is not just an interesting feature of nearby space. It is the reason your brain, right now, has not been shot through at a rate that would leave you cognitively impaired by the age of 40. It is the reason your children will develop normally. It is the reason human civilization has been able to produce culture, memory, complex thought, long-term planning. Every capacity we have depended on a stable biological substrate. That substrate depends on shielding, and that shielding is not paid for. Now here is the pivot. If bodies are this vulnerable, our infrastructure is worse. Because bodies are wet, self-repairing, and evolved for exposure to some radiation. Silicon chips are not. And the machines we have built our civilization on top of are sitting right now in an environment that is measurably becoming harsher. And that has already started to matter in ways that have already cost us money, satellites, and time. Chapter 6. 1007 words. Look up right now. Above your ceiling, above your roof, above the atmosphere, in an orbital shell that ranges from a few hundred kilometers up to about 36,000 kilometers, there are roughly 10,000 active satellites. They handle GPS. They handle weather forecasting. They handle the timestamps that global financial markets use to sequence transactions. They handle military reconnaissance, agricultural monitoring, commercial imagery, television broadcasts, phone calls, internet backbone, aviation navigation, disaster response. They are the invisible substrate of modern civilization, and they are exposed. Every single one of them is sitting inside the same weakening magnetic environment we have been discussing. Every single one of them has a design lifespan that assumes a certain baseline radiation environment. And every single one of them has already, in the last decade, started to show measurable degradation faster than earlier generations. The South Atlantic anomaly is the most visible piece of this. It is a region over the coast of Brazil and the South Atlantic Ocean where Earth's magnetic field is weakened. Not gone, weakened. In that region, the inner Van Allen radiation belt dips closer to Earth's surface, which means satellites passing through it, especially in low Earth orbit, encounter significantly higher particle fluxes. The Hubble Space Telescope has been shutting down its most sensitive instruments during SAA passages for its entire operational life. The International Space Station experiences elevated radiation exposure for its crew during SAA transits. And commercial satellites lose bits, log memory errors, and occasionally suffer permanent damage from single event upsets while passing through it. ESA's SWARM mission, 3 satellites launched in 2013 to measure Earth's magnetic field, has documented what was suspected. The SAA is growing. It has expanded westward across South America. Some analyses suggest it may be starting to split into 2 lobes. And the overall geomagnetic field strength has declined by roughly 9% over the last 200 years. 9% in 2 centuries. That is not a slow trend. Now translate that. Earth's magnetic field is generated by fluid motion in the outer core, thousands of kilometers below your feet. The field is what deflects most of the solar wind and shields the atmosphere from being stripped by the sun's plasma. Weaken that field, and the atmosphere becomes progressively more exposed. Not overnight, but cumulatively. Mars almost certainly had a magnetic field once, and lost it, and lost most of its atmosphere afterward. That is not the same physics as Earth. But the causal link between magnetic shielding and atmospheric retention is real, on very long timescales. More immediately, weakening the field weakens satellite safety, aviation safety, and power grid safety. Because the same field that deflects charged particles also modulates how much solar activity can penetrate to the surface. And here is where history should stop being reassuring. On the night of March 13, 1989, a solar coronal mass ejection struck Earth's magnetic field. Within 90 seconds, the entire Hydro-Quebec power grid collapsed. 6 million people lost electricity. Some parts of the grid stayed down for 9 hours. The event was caused by geomagnetically induced currents, which are electrical currents pushed into long conductors, like transmission lines, when Earth's magnetic field is rapidly deformed by a solar storm. Transformers in the grid saturated and failed. Some had to be replaced. The economic damage was in the hundreds of millions of dollars. That was 1989. That was one province of Canada. That was a solar storm rated only moderately severe by modern standards. In late October 2003, a sequence of solar storms known as the Halloween storms hit Earth over about 2 weeks. Multiple satellites were damaged. The Japanese Midori 2 satellite failed completely. Numerous other spacecraft went into safe mode. Airline flights over the poles were rerouted because of increased radiation exposure. GPS accuracy degraded. Total estimated economic impact was in the range of $10 billion, though full accounting was difficult. And here is the number that matters most. Modern reinsurance industry estimates, from firms like Lloyd's of London and Swiss Re, place the potential cost of a Carrington-class event, a solar storm on the scale of the one that hit Earth in 1859, at between $1 and $2 trillion in the first year, with recovery timelines of 4 to 10 years. Trillion, not billion. In 1859, the Carrington event set telegraph stations on fire. It caused auroras visible in the Caribbean. It induced currents strong enough that telegraph operators could disconnect their batteries and still send messages using only the ambient electrical current in the wires. In 1859, that was an interesting anomaly, because there was essentially no long-conductor electrical infrastructure to damage. In 2026, in a world where every single system we depend on runs through wires, satellites, and electronic timekeeping, a Carrington-class event would be a civilizational trauma. Not extinction, not collapse, but months to years of degraded services, power outages, water treatment interruptions, financial system disruption, aviation grounding, communication breakdowns, all at once. We know these events happen. We have geological and historical records of a Carrington-scale event roughly every 100 to 200 years. The last one was 167 years ago. We are inside the window. Now stack the pieces. The magnetic field is weakening. The heliosphere is variable. The local bubble is expanding, which over long enough time will thin its interior further and shift shielding conditions. Our infrastructure sits above the atmosphere in unprecedented density. Our economy runs on timing signals measured to nanosecond precision. Every system we have built has been built during a shielding window that our children will not necessarily inherit. The reinterpretation is this. The bubble does not just protect biology, it protects the economic substrate of modern civilization, and it is thinning during exactly the century in which we made ourselves most dependent on it. You would think, given all this, that agencies and governments would be shouting about it, making it a headline priority, restructuring infrastructure to be resilient, communicating openly with the public about the timeline of risk. They are not with the volume the physics deserves, and that silence is not an accident, it is a structure. Read enough peer-reviewed papers on space weather, heliophysics, and radiation biology, and you notice something. The language inside the papers is much sharper than the language in the press releases that describe the same papers. And the language in the press releases is much sharper than the language in the news articles that describe the press releases. And the language in the news articles is dramatically softer than the language in the original papers. This is not a conspiracy, it is a compression cascade. And it is producing a public understanding of these issues that is materially different from what the specialists actually think. Let me give you examples. A NASA Human Research Program document on Mars mission radiation exposure describes the current state of the field as involving, quote, unacceptable levels of risk that exceed permissible limits by significant margins, unquote. That is the technical document. The press-facing version says, quote, NASA continues to develop innovative solutions for the radiation environment of deep space, unquote. Same underlying reality, very different effective content. An ESA scientific report on the South Atlantic anomaly discusses the growth of the anomaly and its potential connection to changes in the deep core dynamics of Earth, and includes uncertainty ranges that leave open the possibility of a significant field weakening on shorter timescales than historical averages would suggest. The press summary describes the finding as, quote, fascinating new insights into the dynamic nature of our planet's magnetic field, unquote. The peer-reviewed literature is full of words like unprecedented, anomalous, unexpected, concerning. The public communication is full of words like intriguing, remarkable, exciting frontier, ongoing research. Why does this happen? Nobody is lying. What is happening is more subtle. Funding for space agencies depends on public support. Public support depends on excitement. Excitement is maintained by wonder framing. Warning framing, even when accurate, reduces excitement over time. So, institutional communication officers learn to select the excited half of the papers and downplay the concerning half. Not deliberately, just naturally, over decades, through selection pressure on what gets shared. Science journalists take the softened press release and soften it further. They frame progress over constraint. They cut the qualifiers. They cut the uncertainty ranges. By the time the public sees it, the story is a small, warm, hopeful update in the ongoing narrative of human progress. And when that public later encounters a version of the story that includes the harder details, They experience it as alarmism, because their baseline expectation was wonder. And now someone is telling them the truth is more difficult than wonder, and the emotional recalibration feels like being lied to. That is the trap. The public was given a soft version, and now the sharp version sounds untrustworthy by comparison. Here is where I want to be very clear about what I am not saying. I am not saying scientists are dishonest. They are not. The papers are published. The data is available. Anyone can go read them. I am not saying space agencies are villains. They are, in most cases, doing extraordinary work with limited resources under enormous political and budgetary pressure. I am not saying journalism is corrupt. Most science journalists are trying to serve their readers under intense economic constraints. What I am saying is more structural. The public interface of science was optimized over decades for wonder rather than warning. And in a period when the warnings are becoming more scientifically defensible and more numerically severe, the optimization for wonder becomes a form of misinformation by omission. Not because anyone chose it, because no one chose to change it. The result is a public that thinks space is empty and safe, that thinks radiation is a solved problem, that thinks the magnetosphere is stable and eternal, that thinks the heliosphere is a background feature rather than a variable, that thinks the local bubble is a footnote rather than a moving structure. And then when a paper like Zucker 2022 comes out and quietly documents that our local shielding environment is expanding, is dynamic, is not eternal, the paper gets absorbed into the wonder narrative, and the actual implications never land. Now here is the harder question. What happens in a democratic society when the specialists know something and the public does not? Nothing catastrophic in the short term. But over decades, it degrades the quality of political decision-making. Because policy gets made based on public understanding, and public understanding is downstream of communication choices, and communication choices are downstream of institutional incentives. Infrastructure hardening against space weather has been repeatedly recommended by scientific bodies for over a decade. It has been repeatedly underfunded. Not because it is unaffordable, but because the political will is not there, because the public urgency is not there, because the public is not aware of the risk. That is a communication problem with real-world consequences. Every year we delay significant investment in grid resilience, satellite hardening, and space weather forecasting is another year we roll the dice on a Carrington event, finding us exactly as unprepared as we currently are. Here is the blunt verdict. The physical reality of our shielding environment is harsher than the public framing. The gap between what specialists know and what the public understands is now large enough to have practical consequences. And closing that gap is not a job that the current institutional structure of science communication is designed to do. Which brings us to the bigger question. If this is what we are not being told clearly, what is the actual scale of the thing we are inside of? Because the bubble is not the whole story. The bubble is a symptom of something considerably larger. And that is where the picture stops being about our local address and starts being about our long-term future in the galaxy. Zoom out, widen the frame past the local bubble, past our neighborhood, past the last 1,000 light years. Look at the Milky Way from above, from the perspective of a modern radio survey or a high-resolution simulation of galactic structure. What you see is not smooth. It is not a gentle disk of evenly distributed stars and gas. It is a foam, a network of overlapping cavities, a Swiss cheese structure carved by generations of massive stars, living and dying across hundreds of millions of years. The local bubble is one of them. The Loop 1 superbubble, immediately adjacent to us, is another, and its wall is thought to be interacting with ours along a compressed shell of gas and dust. The Orion Eridanus superbubble is a third. There are dozens of these features in the disk of our galaxy, mapped to varying degrees of precision. Some are old and cooling. Some are young and still expanding rapidly. Some are merging with their neighbors. This is not a bug of galactic evolution. It is the process. Which means what we are living inside of is not a rare or protective feature. It is one instance of a common structural pattern. Stellar violence at the scale that carves cavities like ours, is not a once-in-a-galactic history event. It is the ordinary weather of the Milky Way, distributed across space and time. Our particular cavity, our particular era of relative quiet inside it, is just our position in the pattern, and our position is moving. The solar system, on its orbit around the center of the galaxy, travels at roughly 230 kilometers per second. It completes one full orbit every 220 to 250 million years. Over that timescale, it moves through many different galactic environments. It passes through spiral arms, where star formation and supernova rates are elevated. It moves through interarm regions, where things are quieter. It drifts vertically through the galactic disk, above and below the midplane, on shorter cycles of tens of millions of years. Every one of those regions has a different interstellar medium density, a different supernova rate, a different galactic cosmic ray flux, which means Earth's radiation environment is not constant on geological timescales. It is a function of where the Sun happens to be in its galactic journey. Now zoom into the shorter timescale. The Sun entered the local bubble roughly 5 million years ago. But within the bubble, it is not just floating aimlessly. It is moving at about 25 kilometers per second relative to the surrounding medium, in a specific direction called the solar apex. And within the last 60,000 years or so, the Sun has entered a smaller, denser region within the bubble called the local interstellar cloud. This is a wisp of neutral hydrogen and helium, only about 30 light-years across, with a density roughly 10 times higher than the surrounding bubble interior. Still very low by galactic standards, but higher than what we experienced before. Entering the local interstellar cloud is estimated to have compressed the heliosphere slightly. We have no direct measurements from before we entered it, because Homo sapiens as a species is younger than that transition. But models suggest it did affect the cosmic ray flux at Earth, potentially contributing to slight changes in atmospheric radiocarbon and beryllium production over the last few tens of thousands of years. Read that again. Our species evolved during a window that includes a boundary crossing between two different interstellar environments. We may have already lived through one shielding transition without knowing it, and there are more clouds ahead. Astronomers have mapped several additional interstellar clouds in the solar system's forward path. Depending on which models you trust and how precisely we can predict the Sun's trajectory over long timescales, the solar system may enter another denser cloud within the next 10,000 to 50,000 years. Possibly sooner. The exact geometry is uncertain because the clouds themselves are moving relative to us and our maps of them are still rough. If we enter a sufficiently dense cloud, meaning one with densities on the order of hundreds of atoms per cubic centimeter, rather than the fractions of an atom per cubic centimeter we currently experience, the heliosphere would compress substantially. Some models suggest it could compress inside Earth's orbit. That would mean Earth, for the duration of the passage, would sit unshielded in raw interstellar medium, exposed to the direct galactic cosmic ray flux and to whatever neutral atoms and dust the cloud carries. Now, the timescale here is not imminent in human terms. 10,000 years is longer than recorded history. 50,000 years is longer than modern humans have existed in their current cognitive form. But it is not long in geological or evolutionary terms, and the fossil record suggests it has happened before. The iron 60 layers Wallner and colleagues found in ocean crusts, dated to 2 to 3 million years ago and again to 6 to 7 million years ago, correspond roughly to the era when the solar system was entering the local bubble. Some paleontological analyses have noted that a mass extinction event in the marine record, called the Pliocene marine megafauna extinction, roughly coincides with the more recent iron 60 layer. The causal link is disputed, but the temporal correlation is real, and the mechanism, elevated cosmic ray flux, ionization of the atmosphere, disruption of the ozone layer, increased mutation rates, is at least plausible. The reinterpretation is this: what we call a hole in space is not a special place. It is one weather pattern in a galactic climate, and climate always changes. Sometimes slowly, sometimes catastrophically. Always on timescales longer than human memory, but shorter than geological indifference. We tend to think of Earth's environment as internal. Weather, oceans, atmosphere, tectonics, all of it self-contained. But the outermost boundary of our environment is not our atmosphere. It is not even our magnetosphere. It is the heliosphere. And the heliosphere is embedded in an interstellar environment that changes on timescales our civilization is not built to track. Which brings us to the final question. What does all of this mean for the species standing on this rock, right now, planning centuries ahead as if the shielding budget were fixed? Here is the verdict. Compressed. Consolidated. Read carefully. The local bubble is real. It was mapped in 3 dimensions by the Zucker 2022 paper using Gaia satellite data, and its walls are still expanding at roughly 6.5 kilometers per second. Our solar system entered it roughly 5 million years ago and will exit some region of it into denser interstellar medium on timescales that could be as short as tens of thousands of years or as long as millions, depending on the geometry. The heliosphere, our second layer of shielding, is variable in size and shape. It weakens during periods of low solar magnetic activity. Voyager 1 and Voyager 2 measured cosmic ray flux, jumping by more than 20% the moment they crossed its boundary in 2012 and 2018. Our knowledge of its full 3-dimensional structure is still incomplete. Earth's magnetic field, our third and innermost layer, has weakened by approximately 9% over the last 200 years. The South Atlantic anomaly, the region of greatest weakness, is growing westward at roughly 20 kilometers per year and may be beginning to split structurally. ESA's Swarm mission has documented these changes continuously since 2013. Our civilization sits above an atmosphere it evolved to survive under, but our infrastructure, 10,000 active satellites, global power grids, precision timing systems for finance and navigation, lives in the danger zone. A Carrington-class solar storm today is estimated by reinsurance modeling to cause between $1 and $2 trillion in first-year damage, with multi-year recovery. The last such event was 167 years ago. We are inside the statistical window for another. Every ambitious plan for human presence beyond low Earth orbit, Mars missions, lunar bases, asteroid mining, permanent settlement, depends on radiation numbers calibrated during the best shielding window our star has offered in millennia. Those numbers are variables. They can rise. When they rise, biology and electronics suffer disproportionately, because the most damaging component of galactic cosmic rays scales worse than linearly with shielding degradation. The public communication of these facts across NASA, ESA, and the science journalism ecosystem has been consistently softer than the peer-reviewed literature warrants, not through dishonesty, through decades of institutional selection for wonder over warning. The result is a public that plans its next 100 years as if the shielding budget were fixed. It is not. That is the case. That is what the evidence supports. That is the version of the story the press release did not lead with. Now let me strip away the last comforting illusion. The story most people carry is that space is empty, Earth is protected, and progress is inevitable. That story is not entirely wrong, but it is missing 3 critical qualifiers. Space is scarred, not empty. Earth's protection is a temporary configuration of overlapping variables, not a fixed feature. And progress is a race against a shielding budget we did not know we were spending. The void you have been living inside your entire life is not a void. It is a fading blast wave, 14 million years old, carved by 15 stars that died so that the interstellar medium of our neighborhood could clear enough for our solar system to eventually settle into the calm interior. You are exactly as old as its current stillness. Your parents are as old as its current stillness. Human civilization is as old as its current stillness. Your grandchildren may not be. Now the fairness clause, because I want the case I have just made to hold up under scrutiny. I am not saying exploration should stop. Exploration is one of the few activities that has, in the long run, delivered real information about our position in the universe. Without space exploration, we would not have Voyager's Heliosphere data, we would not have Gaia's map, we would not know any of this. I am not saying scientists are lying. They are, if anything, being too polite. The papers are honest. The compression happens downstream. I am not saying the sky is falling next Tuesday. Nothing about this analysis implies imminent catastrophe on human timescales for most of the risks I have described. Solar storms are the exception, because Carrington-class events are statistically due within centuries and could arrive within decades. But the deeper shielding transitions are slower, not lifetime slow, civilizational slow. What I am saying is this: the physical reality of our position in the galaxy is harsher than the framing most people use to plan their lives. And that framing is what most political decisions, most infrastructure investment choices, most educational curricula, and most public conversations about the future are built on top of. When the framing is off, the decisions built on it are off. And the correction is not going to come from the institutions whose incentives created the framing in the first place. It has to come from public understanding, from people, individually, choosing to know the harder version. The narrow hope is this: we are the first generation with the instruments to see the bubble, map it, measure it, and understand our position inside it. The Gaia satellite, the Voyager probes, the IBEX and swarm missions, neutron monitors, cosmic ray observatories, radio surveys. None of this data existed a century ago. We are the first humans with the actual picture. That is not comfort. It is not reassurance. It is responsibility. What we do with that map, in the next 50 years of accelerating magnetic decline, in the next 500 years of heliospheric drift, in the next 50,000 years of interstellar cloud transitions, determines whether the species survives its own address in the galaxy. Not survives spectacularly. Not survives triumphantly. Just survives. Continues. Passes the information forward to the next generation of people who will need to keep looking, keep mapping, keep hardening the infrastructure, keep understanding. The hole in space is not the threat. The hole is what has been protecting us. The threat is that we mistook it for home.